Welcome to the AP Chem channel, where we help you learn chemistry the easy way by showing you how to solve problems. Today our video is on the solutions to the free response questions on the 2019 AP test, AP Chem test. After every AP test every year, the questions for the free response part of the test are published, so you can always find the questions at the AP website. So if you haven't got the questions yet, please go and download a copy of the questions, and then you can come back and look at the solutions. But if you have the questions already, you can look at the questions yourself, and we can look at the solutions now. Question number 1 on the 2019 AP Chem test has to do with this molecule called urea. I'm going to draw the structure again. It's given on the test in the question. So this molecule is called urea. And part A in number 1 asks you to figure out the hybridization of the valence electrons around the carbon atom in this molecule. So if you look at the molecule, the carbon atom is bonded to the two nitrogens around it, and then also to the oxygen. So let me just draw that part of the structure so that you can see what I am talking about. So in this case, according to VSEPR, in order to figure out the geometry of the bonds around the carbon, we have to find the number of electron domains surrounding that carbon atom. And a single bond counts as 1. So these two count as 1. And each one counts as 1. So, and the double bond counts as another 1. So in this molecule, around the carbon atom, there are 3 electron domains. And according to VSEPR, then the geometry around that carbon atom would be trigonal planar. And in order to support a trigonal planar geometry, the valence atomic orbitals on the carbon must rehybridize to facilitate that geometry around the carbon atom. And so to do that, the carbon must be sp2 hybridized. Okay, so for part 2, there is a picture given in the problem. So I'm going to roughly try to reproduce that picture. So in that picture, we have a urea molecule that's shown inside the solution, and I'm going to draw the urea molecule first. So this is carbon. In the problem, that is black. This is oxygen. In the question, this is an open circle, and there are 2 nitrogens bonded to the carbon. And in the problem, these 2 nitrogen atoms have lines going through the circle. And now finally, the 2 nitrogens are bonded each to a hydrogen atom. So this is the urea molecule. The problem also shows a bunch of water molecules around that urea molecule. So again, red is oxygen. So I'm going to draw all the oxygens first. And of course, each oxygen is bonded to 2 hydrogens in each H2O molecule. So this is the picture that is shown on the test. You notice that the colors that I am using are the standard colors that are typically used to represent these atoms in chemistry. Red for oxygen, blue for nitrogen, black or gray for carbon, and white for hydrogen usually. So in order to form a hydrogen bond, you must have two molecules that on one of them you must have an O or an N that has a lone pair available on that atom in the molecule, and on the other molecule that's making a hydrogen bond to that must have either an OH bond or a NH bond or an HF bond. So you see in this case, the atoms that are acting as hydrogen bonding acceptors are these oxygens, whereas the atoms that are acting as hydrogen bonding donors are these nitrogens. So this nitrogen right here are the donors. So I'll write H bond, hydrogen bond donors. And the oxygen atoms can act as H bond acceptors. But in order to do that, the hydrogen bond must be made such that the hydrogen bonding donor acceptor has a hydrogen between them. So the geometry must be right in order to facilitate the hydrogen bond. So you see in this case, this is the right geometry. This oxygen right here can accept the hydrogen bond from that nitrogen via the NH bond that is on the urea molecule. If you look at the picture, you can see two other positions where the hydrogen bond can be made, just like the other one. However, this fourth one, the position of that oxygen, of that water molecule, cannot be used to make a hydrogen bond, because in this case, this water molecule is not oriented in the proper way such that the donor is pointing at the acceptor. So you see in this case, this will not make a hydrogen bond with the urea molecule. So I think on the AP test, they are going to assume that either one of these three is acceptable. You are asked to provide only one dashed line. For question number C, you need to figure out the solubility of urea at 20 degrees Celsius based on some of the numbers that are given in the problem. So before I do that, let me just rewrite the chemical equation just so we know what we are dealing with. So in this case, the equation is urea, which is a solid, is dissolved in an aqueous solution. So on the left-hand side, we have solid urea, and on the right-hand side, we have aqueous urea. This is an equilibrium. You can actually write down an equilibrium constant for this, and the equilibrium constant for this is just the urea concentration in the aqueous solution. The reason is because the solid urea on the left side of the equation has no concentrations, and so as a result of that, it doesn't appear in the equilibrium expression. So the problem tells you that you can dissolve a maximum of 5.39 grams of urea into a volume of water that is 5.00 milliliter, and temperature is 20 degrees Celsius. You are given that the molecular weight of urea, sometimes that's also called the molar mass, is equal to 60.06, and that's gram per mole. Then what you can do is to calculate the concentration of the solution that results from that. So that's a fairly straightforward calculation, because all we would need to do is to calculate the number of moles based on the mass. So here's the mass. So the number of moles of urea must be equal to the mass divided by the molecular weight. And so when you do that, you will see that this is 0.08974. You see that the number of significant figures should really be 3. So I'm keeping 4, so the last one isn't. The last one isn't going to be significant, but I'll just keep one more just in case. So now what we can do is to then take the number of moles that is calculated right there and use that to calculate the concentration of the resulting solution. So the urea concentration in the aqueous solution is just equal to the number of moles divided by the volume. The volume is 5.00 milliliter. A milli is 10 to the minus 3, so that is 5.00 times 10 to the minus 3 liters. And so when you do that calculation, that will give you the molarity of the resulting solution in mole per liter, or molar. And the correct answer at the end is 17.95. As I've said, the last digit isn't significant because we really should only have 3. So I'm going to just keep 3, and that means I round up and get 18.0. So that's the solution for part C. And now part D tells you that the solubility at a different temperature, so the part C is at 20 degrees C, and part D is at 25 degrees C. And it tells you that the new solubility at this higher temperature is 19.8 molar. And so you saw that at 20 degrees C, it was only 18. However, at a higher temperature is now higher. So this has to do with Le Chatelier's principle, because the solubility reaction is really an equilibrium. So earlier we looked at this equilibrium expression for the dissolution of urea into an aqueous solution. So you see that essentially this is the equilibrium constant, because the concentration of the saturated solution is in fact just K. So what that means is that the equilibrium constant at 20 degrees Celsius is smaller than the equilibrium constant at 25 degrees Celsius. So what that means is that when you raise the temperature, the equilibrium shifts to the right because it dissolves more. So if you think about that, you can think about heat, or the heat of reaction, as either a reactant if it was an endothermic reaction, or as a product if it was an exothermic reaction. So raising the temperature is essentially making more heat available. So if heat is on the reactant side, then when you raise the temperature, it's going to shift to the right. So if heat was here on the left side, then raising the temperature is going to shift the reaction to the right, because raising the temperature is making more heat available. And that is precisely what's happening here, because between 20 degrees C and 25 degrees C, the solubility is increasing from 18 to 19.8. So what that means is that this must be an exothermic, this must be an endothermic reaction. So part E, I'm not going to redraw all the pictures, but essentially the question is asking, what kind of measurements do you have to make in order to measure what is called the molar heat of solution? So let me write that down first, and I'll explain what that means. The heat of solution is a delta H, the change of enthalpy, of the dissolution reaction. So we've written down this reaction right here. And so the delta H for this reaction is called the heat of dissolution because the reaction is dissolving urea into an aqueous solution. So essentially what we are asking is what is the heat of solution here? And to measure that experimentally, what you will need to do is to dissolve 1 mole of urea into a certain amount of solution. To make a 1 molar solution, you would have to dissolve 1 mole of urea into 1 liter of water. And during that, you need to measure the amount of heat that is either going into the reaction or coming out of the reaction. In this case, we see that it's actually an endothermic reaction. So if you do this experiment, the temperature of the solution when you dissolve urea would actually go down because it's endothermic. It takes heat to dissolve the solid urea. But basically, the procedure is as follows. What you're doing is that you have a certain amount of water. So let's say you have 1,000 milliliter, which is equal to 1 liter. In the picture, there's no volume measurement device. There's only a balance, so you can measure the mass. So what that means is that to get a 1 liter volume of water, you need to weigh out essentially 1,000 grams because the density of water is 1 gram per milliliter. So to get 1,000 milliliters, you will measure out 1,000 grams in terms of mass. At the same time, what you need to do is to measure out a 1 mole of the urea. So let's say that is 1 mole of it. And you need to then just dissolve that into this 1 liter of water. And the molecular weight of urea, as you saw above, was 60.06 grams. So to get a mole, you measure out 60.06 grams of urea. And what you need to do is to measure the temperature change of the solution. What that means is that you have to put a thermometer into the solution and you have to measure the temperature of the solution before you dissolve the urea. I'm just going to call that T init, the initial temperature. And you also have to measure the final temperature in order to measure the temperature change. And then you can use this heat capacity equation to calculate the amount of heat that is absorbed by the solution. So delta H is equal to the mass times the specific heat capacity multiplied by the temperature change. Now, of course, the temperature change is just T final minus T initial. So you have to make at least those 4 measurements. So let me highlight them again, just so 1, measure out the mass of water. 2, measure out the mass of the urea. 3 and 4, measure the initial and final temperatures of the bath. Okay, part F. Part F has to do with the entropy. So it gives you a table for the entropy of both the reactant and solid. So let me just write down the numbers. So this is urea solid. The problem tells you in this table the entropy per mole is 104.6. The units are joules per mole per K. So this is the typical units, SI units for the entropy. So this is the entropy content of solid urea, and you are trying to calculate the entropy content of the dissolved urea, and the problem tells you that the delta S of this reaction, so the delta S of solution is equal to 70.1 joules per mole per K. And so what you want to do is to find out what is the S0 for urea. So to calculate delta S for reaction is fairly simple, because this is delta S equals to the sum of the entropy of all the products, and subtracted from that the sum of all the entropies of all the reactants. The delta S for the reaction in this case is given 70.1. The delta S, the entropy content of the reactant is also given. There's only one, which is just the solid urea, and that is 104.6. And this is the number we want to calculate, the number in question mark. So you can easily just do the arithmetic. And so you find that the S0 for urea aqueous is equal to essentially just the sum of these two numbers, which is 174.7, and the units are joule per mole per K. So now part G asks you to explain why the delta S of this reaction is this way. So you see the delta S of this reaction is positive right here. And so the question asks you to use particle level logic to explain that. That basically just means molecular level. So what we have originally was urea that is inside a solid, and we know that inside the solid the atoms are arranged in sort of a regular fashion into sort of like a crystal. So the solid is essentially a bunch of urea molecules all packed regularly together. But when the solid is dissolved in an aqueous solution, what you will have in the solution is a bunch of urea molecules, but now they are dispersed. So they are now no longer stuck to each other because they are dissolved in this aqueous solution. So during this process, obviously, the entropy of a dissolved solute is higher than the entropy of a bunch of solid in a confined arrangement. So in this case, the delta S is supposed to go up. So finally, part H asks you why this particular delta S is favorable for the reaction. So in general, we know that something that has a delta H larger than 0, that is a positive, a delta S. A positive delta S will make the reaction more spontaneous compared to a process that has a negative delta H. So this is more spontaneous. If you want to write this down in the form of an equation, then the delta G is the thermodynamic quantity that controls the spontaneity of a reaction. If the reaction is spontaneous, then delta G must be negative. Delta G, we know, is composed of two factors or two terms. The first one is the enthalpy of reaction delta H, and the second term is the delta S, but the delta S is multiplied by a T. So we have the delta S0, but that's multiplied by this T right there. So this T in the equation for delta G is the absolute temperature, meaning that this is the temperature in Kelvin. So we know that the absolute temperature is always greater than 0. And so in this case, if delta S is also greater than 0, let me indicate that. So if delta S is positive and T is positive, then there's a negative sign, so that's clearly negative. So multiplying all three together, you see that the second factor will give you an overall negative contribution when delta S is positive. And so as a result of that, that would make delta G more negative, and hence it would make the reaction more spontaneous or more favorable. Okay, so that's it for number 1, and in the next video we will go to the solutions for question number 2.